Hello everyone, welcome for this lecture. Okay, today we are going to move to the module 5, that is power system stability. Let's see the introduction of this. Okay, let's define what you mean by stability. Okay, remember stability of the power system is stability is nothing but the ability of the power system. Okay, stability is the ability of the power system to retain its under normal condition. Okay, so even though fault occurs on that, okay, that is called a stability. Okay, so this one will be we can define it in systematically that saying ki stability of a large interconnected power system is its ability to retain to a normal or stable operation after having been subjected to some form of a disturbances. Okay, though therefore this will result in conversely instability denotes a condition of loss of a synchronism in the system. Okay, obviously, right? So and then this will result in wild fluctuation of a current and voltages, right? Current and voltages within the power system network, which is obviously undesirable. Hence stability consideration form an important aspect. Okay, this is a very important aspect in the study of a power system. Okay, we'll see the few definition of this under this stability. We'll use the stability, and we use the steady state stability, transient steady state stability, dynamic stability, steady state stability limit, transient stability limit, and infinite buses. Let's see one by one. Okay, stability, as we have discussed, stability is the ability of the power system. Okay, let's define it in a proper way. Stability, when used the reference to a power system, it is the attribute of the system or a part of the system which enables it to develop a restoring forces between the elements thereof equal to or greater than disturbing forces. Okay, obviously if you consider this as a factor, ability of the system will be greater than that of your fault whatever occurs on the power system. Okay, then let's see what you mean by steady state stability. Okay, as we have discussed, stability is the ability of the power system to retain under normal conditions. Okay, remember stability will be greater than that of your fault in general, if you'd like to speak, it should be. Okay, if not, then the restoration works has to be start, corrections and all, right? Next let's see deal with the steady state stability. Okay, this is the stability of the system under consideration subjected to a gradual or relatively slow change in load. Okay, very a small or slow change in load, right? Next we'll see the transient state stability. This refers to the stability of the system subjected to a sudden large disturbances, as we have studied this one in symmetrical faults as well. Okay, right, where during sudden disturbance, the large disturbance may be brought about by sudden large change in the load, faults in the system, or loss of generation in the system. Okay, next move to a dynamic one, dynamic stability. This denotes the artificial stability given to the system by the action of automatic control device like a fast acting voltage regulator, or and you can say for governors also. These are all your dynamic stability. Okay, and then next one is steady state stability limit. This refers to the maximum flow of power possible through a particular point. Meaning of this one is at what angle the maximum power you get. That is the limit of your steady state stability. Okay, and then transient stability limit we'll see. Okay, this one is also it refers to the maximum flow of power possible through a particular point without the loss of stability when the sudden disturbance occurs. Okay, and last one is infinite bus. Okay, this is a system having a constant voltage and a constant frequency regardless of the load on it is called as infinite bus bar system. okay, or you can say it is an infinite bus. Physically it is impossible to have an infinite bus bar system. This is just a consideration for the purpose of analysis. Okay, I hope for this infinite bus you would have seen in the in fourth semester lab or third semester lab, synchronization when you are doing of machine, synchronous machine, there you would have used this infinite bus bar connection. Okay, now let's deal with the first one, that is here we are going to study first one is steady state stability and transient stability. Okay, first one, let's deal with this steady state stability. Okay, the steady state stability is basically concerned with the determination of maximum power possible through the power system. Okay, without a loss of synchronism. Okay, without loss of synchronism is nothing but your stability. Okay, this formation of a power angle equation plays a vital role in the study of steady state stability. Okay, we'll see this, since it plays a very important role, we'll calculate what is the power angle equation of a synchronous machines. As we know, the synchronous machine is one of the most important element of a power system. A synchronous generator converts mechanical power into electrical form. Okay, okay, and feeds it into a power system network. Right. On the other hand, you can say about the motor, synchronous motor draws electrical power from the network and converts it into a mechanical form. Okay, there are basically two types of synchronous machines. One is your non-salient pole machine, another one is a salient pole machine. Okay, let's deal with the one. Okay, first we'll deal with the non-salient pole synchronous machine. Let's see power angle equation for that. Okay, let's consider in this case. Okay, in this case of a non-salient pole machine. Okay, so the rotor consists of a cylindrical structure. We have studied its construction and all, right? Cylindrical structure having a number of slots at intervals along the outer periphery of the cylindrical, okay, for accommodating the field coils. Hence the air gap is uniform or all along the rotor periphery, and hence the flux linkage is also uniform. Therefore the machine offers the same reactance for flow of armature current at all the places. The reactance is called as the synchronous reactance of the machine. Okay, so let's see, it's a single phase equivalent reactance diagram. Okay, this is your synchronous machine, means generator, right? And then machine, and then this is your transmission line. Okay, so and this is connected to an infinite bus, right? As we have seen, this is the equivalent reactance diagram. We are very familiar with this. Here these two, okay, synchronous machine, output of this one will be terminal voltage, what we represent. Okay, this is the XC is the transmission line reactance. Okay, so V is, you can consider for infinite bus voltage. Okay, and you can refer this, you can take this as a reference. Okay, I hope you have got this circuit diagram. We'll see, let's take E at an angle delta. Okay, E at an angle delta, this one is your synchronous generator voltage in the machine. Okay, E at an angle is generated as a voltage in the machine. Delta is the load angle, or you can say it is a torque angle. Okay, or you can say it is power angle also, right? Xs is the, which is connected in series with this, is called as synchronous reactance of the machine. Okay, Et at an angle theta can be considered as terminal voltage of the machine. Okay, Xc is the transmission line reactance. Okay, V at an angle 0, we have taken this as voltage at infinite bus, and as I said, you can take it as a reference. I is the load current. You can observe all these are connected in series, so I remains same. Okay, so let's take, suppose that a machine is operating for a lagging power factor. Okay, suppose if it is operating on lagging power factor, then load current lags. okay, lags infinite bus voltage. Okay, so then by an angle phi, okay, it is by an angle phi it is going to operate. The corresponding phasor diagram we'll draw once and let's see. Okay, so as we have said, according to this formula, what is this E? Generated voltage E, obviously E at an angle delta. Okay, so E, if you are taking only magnitude, okay, whatever you are going to consider for the derivation purpose, remember one thing, you are going to take it for a real part. Okay, I don't repeat this, it is we are going to consider only for real parts. Okay, and then now what is the equation for this E? Generated voltage will be equal to, it has to satisfy your means reactance, synchronous reactance and transmission line reactance, as well as this voltage, infinite bus voltage, right? So in this, E will be equal to, I is remains the same, therefore I into x's, okay, plus I into xc, right, and then plus V at an angle 0, right. This is your total voltage, generated voltage. Okay, so then we have to draw this diagram. Okay, for that what we have to do is, let's take, as we have said, we are considering V at an angle 0. This is the voltage at infinite bus, is the reference point. Okay, and current I, okay, current I is lagging, okay, to this infinite bus by an angle phi. Okay, lagging, right. This you can, sorry, this is, I'll show you, this is your V at an angle 0 degree. This is a voltage at infinite bus, and phi is the angle, your current in the system is a lagging voltage by angle phi. For purpose of understanding, I'll expand this line, okay, extend this line. Okay, and then what we can see is shit, I'm sorry, I'll take only one line and then we'll do. Okay, this is V at an angle 0, this is your I at an angle phi. Okay, now as I said, you can expand this line. Okay, and now observe, these all elements are connected in series. Okay, so as you have seen, E is equal to what? I into xs plus I into xe, which is a voltage drop across synchronous reactance, voltage drop across your transmission line, plus V at an angle 0. V at an angle 0 we have got. Now we have to get this and this drop. So Ixs is the voltage drop in the reactance. Remember, voltage drop in the reactance is leads your current, because current remains the same, right? This voltage drop leads the current. So what we can take is, what you have done is this, you have extended the line. That you, what you can do is take this line and extend with reference to this, yes, 90 degree to this. Okay, it is should be on V at an angle 0. Okay, yes, so this is not perpendicular to this line. Okay, this is perpendicular to this line. Okay, voltage drop of a synchronous reactance is leading the current. Okay, and then what about xc? It is also same, it is also leads the current. Okay, it is also leads the current by 90 degree. Okay, therefore this this voltage V at an angle 0 plus I into xs plus I into xe is your total voltage, that is E. Okay, and you would have observed in the circuit you have a ET also. What do you mean by ET? ET is your what is that? Ixs plus E. Therefore this much is your ET. Okay, remember, E at an angle delta means this is the total E. Okay, this is the total E, and then what is the angle made by that is the delta. Okay, and ET at an angle theta means this much is your theta. Okay, I hope you understood this phasor diagram. Let's see this. Okay, same what we have drawn here, right? So it is xs and xc, total is E. Okay, so now what you have to do is, referring to this, phasor diagram, you write what is E is what? Total voltage, that is V plus J into, means like J axis into I plus J axis into E. Therefore this voltage can be written, right? This equation can be written from this equation. Therefore I will be equal to what? E minus V divided by J xs plus Xe. Let's call this equation number 1. Okay, to get the net power delivered by the machine, that can be calculated as P is equal to VI conjugate. Okay, let's call this equation number 2. Substitute equation number 1 in equation number 2. What you get? V as it is. Remember, all these things you have to consider as a real parts. Okay, and then only magnitude you have to consider of all these things, because anyhow voltage angles also they have mentioned V at an angle 0. Okay, I have taken simply V. It should be V at an angle 0. Okay, so now we'll see I in the I place we have to substitute this equation, conjugate of that. Just we have written once again, like observe here, it is E is at an angle delta, right? E is at an angle delta. E is the magnitude, delta is the angle of that. V at an angle 0. X plus Xe, J is there, we can write it as at an angle 90 degree. Okay, we have expressed all in terms of angles, magnitude and angles. Okay, let's see next. Same equation can be taken here. Okay, at an angle, all right, this should be at an angle plus 90. Okay, at an angle plus 90, right? Sorry. And then now we'll see okay, that was correct. It is what conjugate. We'll remove this conjugate. When you remove this conjugate, what is the changes will be takes place? So remember, angles or whatever angles are there, that is going to be change its signs. Okay, so conjugate, if you remember, it will be minus delta. Okay, V at an angle 0 is there, minus 0, anyhow it will be remains the same. And then if you change this value, it will be again minus 90 degree. Okay, remove this conjugate sign. So then take it is minus delta minus 90. All right. Okay, then you can take, what you can do is expand this. Okay, we should be multiplied with this term and we should be multiplied with this term. So V at an angle 0 into E at an angle minus delta divided by xs plus Xe at an angle minus 90, right? Similarly you do this one also. As we said, we are going to consider only real part, means this can be expressed as V into E magnitude divided by xs plus Xe. What about its angles? It has to be taken for a real parts. Cos of this is a minus delta in the numerator, because this minus 90 is in the denominator, so it should be taken as minus of that angle. Minus of that angle is minus 90. Therefore it comes as a 90 minus delta. Okay, and then here if we simplify this, it is minus V square. Okay, xs plus Xe cos of, anyhow its angle is 0 in the numerator, so it is denominator angle is present, so it should be minus of that angle, it is minus 90, so it will be cos 90. Okay, what is the value of cos 90? Cos 90 is 0, so this term is going to be 0, right? Now you consider this equation. So cos 90 minus delta, if you simplify this, then what is the cos 90 minus delta is nothing but your sin delta. Okay, so therefore P is equal to V magnitude E magnitude xs plus Xe sin delta is your power angle equation. Okay, this indicates that your this equation indicates that the power transferred depends on the generated voltage E, bus voltage V, system reactance and torque angle delta. Okay, this equation is called as your torque angle, this equation is also called as power angle, okay, of a non-salient pole machine. Okay, we'll see the power angle curve, that is nothing but your graphical plot of plot showing the vertical variation of electrical power P against the load angle delta for fixed values of E, V and reactance is called as a power angle curve. Let's draw this power angle curve. So it is delta versus P. Okay, if you very systematically, you get a power angle curve of non-salient pole machine. Okay, this one. So here it is a PM, means maximum power. When you get a maximum power in this equation, when you get a maximum value of this, when sin delta is 1. Okay, meaning of this one is when sine delta will be 1 when delta is equal to 90 degree, right? So the time you get a maximum value, therefore you get a maximum power when delta is equal to 90 degree, and at 0 you get a 0, and at a delta equal to 180 degree again also it is will be 0, right? So this condition, if you are writing the maximum power transfer occurs at an delta at an angle, sorry, delta equal to 90 degree, then the corresponding equation we can write as a delta 90 can be put as 1. Okay, VE divided by XS plus XM XC, right? So here um, now, what we can say is for a value of delta greater than 90 degree, okay, if the delta is greater than the 90 degree, the power output of the machine reduces successively and finally the machine may stall. Hence PM at which maximum power transfer occurs is called as steady state stability limit, okay, of the machine. The machine operation, okay, the machine operation is stable in this region, that is delta is 0 to 90 degree, okay, that is analyzed as, you know, the slope of the curve dp by d delta is greater than 0, okay. This term, that is dp by d delta, is called as the synchronizing power coefficient, or we can say machine stiffness, okay. This condition dp by d delta is called as stiffness of the machine. This condition dp by d delta is greater than 0 is called as stability criterion, okay. And then the steady state stability limit is reached when dp by d delta is equal to 0, and if dp by d delta is less than the system is then if you say dp by d delta is less than the 0, then the system is unstable. Okay, I hope clear this, I hope it is clear for all. Then we can take a brief note about this. If at all the synchronous machine is concerned directly to the infinite bus, then xc will be equal to 0. That time your power angle equation will be this one, p equal to ve divided by xs into sine delta, okay. If and what we can say is another one is PM, that is the maximum power, is also called as pull out power of the machine, okay. Thank you.